Once again, for his return engagement, David Dillow from Oak Ridge National Laboratory.
So I'm trying to make up for lost time for missing the first couple of lugs that I could have actually come to. So, pardon me for trying to get going. And, we do seem to be moving pretty quick, and I can really sum us up and get us out of here real quick. So I did a couple of things I found interesting. I got a little bit of modest results out of it, and that's really all I had to say about it. Any questions? So one of the problems we keep running into with Lustre is, we're dealing with these larger and larger systems, and so we're kind of, when we want to do various management operations, we're dealing with this large haystack. It comes down to a key metric for us for how long is it going to take certain management tasks, these common ones that we end up having to do over and over again, is really the number of files that we're dealing with rather than the number of petabytes we're dealing with. Especially when we're talking about the metadata server, 10 petabytes, 20 petabytes, whatever, 100 million files, 10 million files, that's the number we really care about. Generating candidate lists for sweep, I mean, depending on your center, you may have different, different policies for that, but for us, we end up having a 2-week sweep period, and if you haven't touched your files in 2 weeks, we're going to move it off the system, give us some room to keep going. Listing files on an OST when you want to sit down and you want to find out, hey, I need to rebalance my my OSTs, or I've got a bad one that we've had some problems on it. We want to see which files could possibly be affected by any trouble we might have had. And then naming inodes from error messages. Sometimes you get an error message, you need to know, oh, what file is that? And the problem we keep running into, as I said, file systems keep growing. We've got 10 petabytes of aggregate storage. We've broken it up into 3 file systems, and so right now, as of yesterday's numbers, we had 118 million files in one of them. The other 2 had 62 million and 13 million. Now, the one with 118 was our only file system for a while, and you can guess as to which one of the 62 or the 13 million is actually the climate guys. They like lots of small files. Now we're down from peaks. We had over 250 million files in our big one at one point. 109 million, 86 million on the other 2, where we weren't running sweep quite as often. If you may have heard, there was an A-time bug, and users were getting a little upset because, oh, we might have deleted a file after they staged it, but before it ran. A little bit of a problem. Thankfully, that's been fixed, and we got the fix rolled to production. Wait the requisite amount of time, so we're not actually getting rid of a file we shouldn't too late, and we started purging again. So some of the current tools, and some of this is a little bit disjoint. There's not really a great order to go through this. But there's a couple different tools we end up using to manage our file systems. High-level ones, they're often remote. They don't have to be. You can mount a client on your metadata server and run from there as well. And you really recommend having a good amount of memory so you don't run into deadlock situations. But Find and LSF Find, these guys run at the high level. They run on a client. They do RPC calls over to the metadata server, out to the OSTs, depending on what you're trying to do. And then you've got low-level tools that are more direct access. They want to talk straight to the LUNs. These things like debugfs, E2scan, NE2scan, which is Nick Cardo's enhanced version of NE2scan, gives you a little bit more information about the files as it goes through. So I'm going to talk about numbers that we've seen on our systems, and I need to tell you a little bit about our execution environment. So in both cases, both for our production and our test bed, we've got an Ingenio 7900 or an XBB2. And behind that, we have 81 terabyte SATA drives, and they're all in a RAID 10 setup. And they're all short strokes, so we're running this out of a 7.5 terabyte, well, actually it's right at 8 terabyte LUN for the metadata server. In production, we have an additional LUN on those same drives that ends up being an 8 gigabyte journal for us, so we don't actually end up hitting this that often. Production-wise, we're connected with 4 gigabit fiber channel connections, and we're running on a 16-core Xeon box. So it's quad socket, quad core, and we put 64 gigs of memory in that box. Now on the test bed, it's a little more constrained system. We have more. So we've got SRP over DDR InfiniBand, and actually ends up being SRP over QDR InfiniBand to a DDR connection to the XBB2. And we've just got a 4-core Xeon, which is in the Halem box, and this was intended actually to be as a client node for doing I/O testing. We didn't really need a lot of memory in it, so yeah, we'll just put 6 gigabytes of memory in there and we'll run with that. So that actually has ended up affecting my work a little bit. I'll tell you more about that as we go on. The other piece for this, most of these numbers, especially from the test bed, these are from a live snapshot of our production system. I took, and over an 8-hour period, I DD'd basically the MDT directly into my test bed. After I got it in my test bed, I let FS check run against it for about 20 hours to clean up all the inconsistencies that I had, because we've got users doing backup or doing their work as I'm running this. So obviously 8 hours, we're going to have a lot of changes to the file system. So FS check was not my friend that day. There's about 166 million inodes in use. About 150 or so of those were files. So as we said, one of the management tasks, sweep keeps taking longer and longer. Running E2 scan, running an E2 scan for the Widow 1 file system with 150 million files, and this is concurrently with the time that I took this. We were taking 21 hours to generate a candidate list, and this is just running the E2 scan on it. Now, this is a highly variable number I'm giving you. 21 is really at the outset of that. Usually it's more about 10 to 12 hours to actually generate this list. Occasionally we'd see it drop down to 8 hours, so hey, that's a pretty good run. For Widow 2, or the one that has all the climate files on it, about 90 million files. It takes about 6 hours to generate just the file system list, all the metadata, all the file list, using an E2 scan. Occasionally this would bounce up to 18 hours, and sometimes it'd go really fast and it'd come down to 4 hours. So there's a lot of variability in there. And part of that comes into is past usage affects future performance. This is not, I'm not giving you a commercial for stocks up here. No prediction. Actually, there is a prediction here. Part of the reason these things take so long, and they don't necessarily slow down as much when you have a fewer number of files on the system, is that E2 scan and E2 scan are both pretty well optimized. That hey, if in the block group descriptors we can say, I only have to read this portion of this section of the inode table because I know that past that I've not used it yet. I have an area that I know these are completely unused, and so I can skip all of that data and not have to read it. The problem is these guys have gotten really big. The 150 million files, I'm actually scanning 580 million inodes to find that I'm only actually using 166 million inodes. The other problem is, these are production numbers here. Current usage gets in the way. Now, our metadata server doesn't do a lot of I/O. That's one of the nice parts about throwing a lot of memory at it, is that we can stay cache warm for the most part. So I don't have a huge amount of I/O, but I do have I/O from time to time that gets in there and starts affecting things. Also, because any E2 scan uses it goes through the buffer cache, doesn't use O direct. Sometimes we'll run really fast because we get really lucky and all the data we want for an E2 scan is already in my cache. I don't have to read it in again. It's great. So another one we have, finding files on an OST. So we had an issue on one of our on Widow 1 and had an OST problem. And we needed to find out all the files that could possibly have been affected by this. This was live. We actually had more like 250 million files at that time. It took us 5 days to run LFS find to get a list of all the files that could possibly have been affected. As it turns out, running an E2 scan, we could have found that in 3 hours and 20 minutes and parsed through the list. Or well, probably would have been more like 6 hours, given that 3 hours and 20 minutes is 150 million files. And this does include the time to generate that 30 gigabyte list, which, hey, that's not too bad for 150 million files. Some of the things that affect that 3 hours and 20 minutes, we are running over Lustre for this. None of our systems, our servers have local storage other than what's being used for Lustre. So everything has to be, we mount the client system, we write the files out on that, and then we sit there and process it elsewhere. Now, FS Find has a little bit of room for improvement there. If I was to grep through that 150 or that 30 gigabyte file, Lustre can actually handle that in about 2 minutes. So there is some room for us to improve. Then the other one we have, naming an inode. There was a bug at one point where you had issues where if an OST went offline, you could potentially reuse the object IDs. And the file system really does not like that. You start getting a bunch of these error messages. Hey, I tried to pull in this data and I found an existing inode and it's given here, what was that? 10,979,900 in a generation, and I found he already had data, and he already used this object ID that was already in here at 10,979,916. Well, now I've got to go find two files and give a name to it so I can go figure out what user I need to talk to and tell them exactly what's going on and that, hey, you don't want to use that data. This is a call you don't want to have to ever make, but when you do have to make it, you want to make it as fast as possible because you're already in the doghouse. The question is how long you're going to stay in the doghouse. Debug takes about 2 hours to name those files. And this is on the testbed system with nothing else going on. And I'm giving it -C, so I don't sit there and read the bitmaps, which takes a really long time from debug. And I'm giving it all the inodes to name in one shot. So it should actually be able to go through and name these. It should run through the directories, find this, and stop. And actually it takes longer than 2 hours. 2 hours is when it spit it out. It's supposed to stop after it finds the inode names for the ones you gave it. It didn't. And after about 4 hours I just said, fine, I don't really care anymore. I got the data I want. So why aren't the current tools any faster than they are? Client side, all those tools, like I said, round trip latency is causing a problem. The other problem we've got, we are in a situation where we're doing read-only operations to the metadata server, so we should be able to pipeline these a little bit, but these tools weren't written with this in mind, so they don't sit there and try to get multiple threads going, get multiple stats going, that kind of thing, to hide this latency. They're all very serial tools. Another problem we've got, debug, NE2scan, these guys are all built off of libextended2. So we've got poor read-ahead behavior, and we'll talk a little bit more about that. We don't keep a very deep queue. We usually only have one request outstanding at a time, maybe two depending. We have small request sizes. We're usually asking for about 8K at a time. And NE2scan especially, it starts introducing random seeks. And it happens in both phases. And we'll talk about the phases there and we'll go on a bit more about that. So I actually got my slides a little bit out of order, so I'll come back to the one before. So E2scan, the way it works, phase one, we go out and we scan all the inode tables. Let's find out what's interesting to us. So we just do a linear scan of the inode table, and this can actually go really quickly because, hey, big chunks, we could do real large reads. We also sit there for each one of those, we end up iterating the block lists. If we find a directory inode, we say, okay, well, we want to iterate and get all the blocks that are associated with this directory so we can come back later and get the directory contents. So we got a linear scan, and then we got this somewhat random IO component that goes with that. Same thing for phase two. We scan those directory blocks, and we're smart. We sit there and we sort those so that we just do an elevator scan of the disk. And for a simple case, this is great. That's all we do. We build up a path tree. We can name our inodes as we find them when we go on. However, the normal case is that when we're using these tools is we're building a list of metadata for our system as well. And so as we get a name for an inode, we say, well, actually, we want that inode information now, so let's go read it. Okay, and oh, that inode had an external attribute. Well, we need to go read that. And then we come back and we print it out and we go to the next inode. Or we start reading the next directory block. And that really starts to kill your performance. You're seeking all over the place. So what do we really want to do to feed these beasts the way they want? They want really large requests. The bigger we can give them, the better. And the more requests we can keep in flight, hey, this is what we really want. Probably actually want to end up avoiding POSIX fadvise right now. And I'll say it at the outset, really probably part of the proper fix here is to just go fix the kernel so that it does the right thing here. Watching straces on this, fadvise was coming back, and it was taking quite a long time for it to actually run. We're talking about a millisecond or whatever. And you watch it, and it's like, oh, I call fadvise, the kernel goes and reads the file or the block for me and comes back. Well, no, that's not really what we want fadvise to do. We want to say, hey, I'm going to need it in a minute. You do it in the background. Don't make me wait. So if we can improve these IO patterns, we want to use them in other tools. And frankly, I don't want to rewrite libextended2fs. These are kind of the things that, what's driving the direction I chose. So I ended up writing a new IO manager for libextended2fs that uses Linux AIO in the background, so that I can have much more control over what's going on. I use ODirect because I don't want to flush out all the data that's actually in my page cache. I want to keep that there so that I can try to minimize the disturbance to actual IO I'm doing. I don't want to blow away the cache that I already have. I can reuse IO channel read ahead, which is a Lustre addition to extended 2FS, to actually go out and do read ahead. With the Unix IO Manager, that actually ends up calling into POSIX fadvise. With mine, it calls into my library and says, hey, I'm going to want this in a while. I'll get it for you and have it here when you're ready. So I keep an internal cache so I can sit down and say, this is how much memory I want to allocate to going faster. I don't have to worry so much about, am I going to blow everything away from my page cache? I just want to do 20 megabytes or 400 megabytes or ever how much I end up wanting to put to it. And I can kind of control how much I'm going to try to keep in flight. I've got, the defaults are 20 megabytes, 8 requests, and each request is 1 megabyte in size. I keep for most of these numbers, I ended up putting about 380 odd megabytes in the cache and try to keep 64 requests in flight. So just by doing this read ahead, what kind of results did I end up getting out of that? So, first part, inode scan, phase 1. Didn't see a huge, I got 10%. Well, and I'm not doing the block iteration, I'm just doing the inode scan. 10% isn't that great. I'll take the 40 odd seconds that I get back in my life. That's kind of nice, but in the grand scheme of things, it's not a lot. And if I start doing inode iteration, both of them perform the same. I'm 2,400 seconds, so I'm still going to be here for 40 minutes. The directory scan's another area that, hey, this actually works pretty well. On this system with 166 million inodes, 150 million files, there's 80 gigabytes of directory entry data that I have to scan through to be able to put names to inodes. And so just doing the name scan only, all right, I'm taking about 50 minutes with the Unix manager. Well, wait, now I've got a pretty good win here. Now I'm only taking, a little less than 10 minutes. Well, that's a nice win. I like that. But I'm still only doing the name, so maybe we got some more problems here to work out. Like I said with the block IO stuff, we seek around a lot. So the kernel doesn't give me a really good way to address this. So this is another reason I went with the AIO Manager, is I can add some APIs to make things work the way I want them to. Most of the time, I don't need the results from a seek right off. I can call back, let me know when it's convenient and just tell me the data. This means I can sit there, I'm already scheduling my read ahead requests. So now I've got these asynchronous requests I don't care about as much. It's real easy to put those into the stream that I'm already sending down and try to keep that as sequential as possible. So just a real quick high level, I added 3 new functions to the library for doing asynchronous reads. The big thing is it takes a callback, what block number you want to read. I ended up having to put two private data. I hand 2 private pieces of data to the callback. I ended up needing that to implement higher level ones without having to do an allocation for every request I do. And then there's 2 other pieces that allow you to manage what's going on. You can say, well, how many asynchronous events do I have still outstanding in the queue? And hey, I want you to go ahead and start working on those, flush those out, and don't come back until you have at least no more than max requests in the queue. And I'm not really using these all that much right now. The purpose for these is to allow me to, in the future, manage my memory footprint a little bit better. That I can run up until I get to a spot and say, oh, I need to stop for a little while, run these out, and then come back. High level, the 2 big pieces I need is block iterate. Hey, give me an inode. Here's the blocks I want you to tell me about, or tell me all the blocks that belong to it. And this is one of the ones that ended up needing 2 private data. And the same thing for the inode. I want to read this inode. I don't need it right this moment. Just whenever you get a chance, call me back, give me the data for the inode. So the implementation of this was rather naive to begin with. I started with a linked list, and well, that doesn't really work out that well if you're iterating over a couple 100,000 entries in your linked list to find where to insert the next one. So each inode block I'd read it 8 times. So that's kind of a problem when you go from reading 500 or 166 million inodes again. You end up reading 800 inodes. That kind of sucks. We would only read 1 block in each request. And the only good thing out of this was, well, mostly we kept the queue depth high. Except, well, no, we didn't really. CPU usage from the linked list kind of killed that idea. So let's make that a little better. We went ahead and we started. Hey, I'm asking for this block 8 times. Well, maybe I should only send 1 request down to the disk. We started growing things larger into larger and larger requests, and that by itself gave me a 15% wall time improvement on my runs. I also found that, hey, these systems, I'm running with 80 drives in a RAID pair. Maybe I sit there and I can hand them one larger request, and if I throw away, 24, 64K of that request because it was a gap and I don't need that data, well, I don't actually care. I can read extra data. The IOPS is one of my big limitations, not so much the bandwidth. So that ended up giving another 5%. It's a tunable because it's going to depend on your hardware. And I also worked on the cache and the asynchronous bookkeeping to make things a little more efficient for the CPU. So now we're getting a little bit better results. Inode scan, same thing as before, except now we've added the block iteration. Now if I'm just using the Unix manager, I'm doing it in 15 minutes. Now with the asynchronous code, we're doing it in 6 minutes. So that's a nice improvement. I can live with that. You look at this, and I put the NE2 scan number in here to keep me honest. When I'm doing this 80 gig lookup with inodes, the Unix IO Manager, with the same code, almost 51,000 seconds. Well, that looks great compared to 3,000 seconds or 50 minutes. But NE2 scan does it in 14,700 seconds. And the only way, I don't know exactly what's going on there, because I have made some other CPU optimizations to NE2 scan. Odds are good they've increased my latency a bit, and so that really shows up when I'm serialized and only have one thing in flight. But I'll take a 500 or a 50-minute scan on that. That's 3 times better, 4 times better. I'm pretty happy. So, like I said, IO is pretty efficient now, but I'm still seeing stalls in this. There's improvement available. I hit CPU, 100% CPU for a few seconds at a time in the pathname lookup. And so we stopped sending requests. All of the requests came in, and I'm not putting any new ones in because I'm stuck in a loop somewhere. So I kind of get behind. This is where having a larger cache really helps, because you can kind of smooth that out a bit. Did a couple of work there, and this is in the numbers we saw before. I replaced the glib RB tree with the kernel's implementation. We had to, with the glibc one, we have to sit there and walk the tree twice to figure out, oh, it's not there, let me create the entry, and then now I'm going to walk the tree again to actually insert it again. This actually ended up in a micro benchmark, took about 15% of the CPU away, but in the full runs, this ended up actually taking around 16% of the wall time away. That's a nice win just for, let me free up the CPU so I can make sure I keep things going. We improved the path name generation a bit. I don't have to walk the tree, the path tree that we built up multiple times if I'm starting in the same directory. So every time I'm naming one, and it happens a lot because I'll get multiple directory entries per block, that I don't need to rename everything from before it. I know that, well, I stopped at that directory. I already know what the path to that directory is. Let me just print the rest of it. This was 30% in a micro benchmark and about 5% on the wall time. So, on top of the RB tree change. So that's another nice little win. So where are we today? So I generate a full FS list compatible output. And FS list is what I call the output we get from NE2 scan. And there's a suite of tools that Nick put together that parses this kind of data. And that, so part of my goal was to slot into what we use today so that we don't have to change too much. We can kind of go forward with that. So now I can get a full metadata dump, 160 million files or inodes that we go through to actually look at 590 million. I do it in 1 hour on a test bed versus the tools we started with took about 5 hours. On the production side, 119 million files. Took about 30 to 50 minutes for my tool to run versus 3.5 to 8 hours for the tools that I started with. So I'm really happy with the results that we've gotten here. Naming inodes. Fortunately, I don't have to do this much anymore. We found that bug, we fixed it. But should it ever have to happen again, I can name these 3 random inodes in a directory. I can do it in 15 minutes versus the 2 hours with debug FS. The nice part is, hey, that part of my of this tool, it's obsolete. We don't care about it that much anymore. 2.0 is going to make that 30 seconds. So that's a beautiful thing, and I'm happy to be obsolete already. Future work. Well, I'd actually like to give this out to everybody. I really wanted to have this ready so I could sit there and say, hey, go to GitHub right here and download the code and go have fun with it. Unfortunately, life being what it is, yeah, that didn't happen. It's mostly there. I need to add some option processing so that you can do more than my hard-coded things in it. And then I actually have to run it through legal. So, you know, code-wise, yeah, we're talking about a week. Legal-wise, we'll talk in June. It's probably about a realistic expectation for me getting it through the process. Part of this, I want to track down the remaining CPU hogs. Like I said, you know, we can go a lot faster. If I can keep the I/O going, there's no reason we shouldn't be able to get this down to about 45 minutes on the scale of the systems we're talking about, and maybe we can go better than that. Especially if we don't care about the metadata output in the FS list. I mean, naming those inodes versus actually generating a list of the path names, it's going to run about the same time. You can do it in 15-20 minutes. I haven't actually implemented, you know, naming which files are on a particular OST. And I don't have write support, which is kind of a killer thing. Oh, sorry, kind of a killer problem. I think this would be really interesting. We could take FS check, and there's a lot of portions in FS check I think that kids say, well, you know, I don't need this data right off. I do eventually need it so I can get to a consistency check. I'd like to do some work on trying to use that with FS check and see if we can make that faster. You know, no one wants to wait around for a day for FS check to finish. You know, if I could get 3 times speed up, I don't know if 3 times actually matters in that case. What's the difference between 8 hours and 24 hours really? You're down. But, you know, that it is better, so in case of emergency you can get back up later. So those are all the content I had prepared. Does anyone have any questions?